We remember Apollo as the impossible thing humanity pulled off.
All right.
12 men walked on the moon. All of them came home. No one died on the lunar surface. And in the 50 years since the last boot print was pressed into the regolith at Taurus Littrow, Apollo has taken on the quality of legend. Something dangerous, yes, but ultimately triumphant. A story with a good ending we've told ourselves so many times, it has started to feel inevitable. It was not inevitable, it was extraordinarily close to catastrophe on multiple occasions. And the version of lunar exploration we are now building, the Artemis program, is in several critical and measurable ways more dangerous than Apollo ever was. That is not a criticism of NASA. It is not an argument against going. It is simply the truth about what it means to push further than we have ever gone. Stay longer than we have ever stayed, and attempt things that Apollo never attempted and was never designed to attempt. Apollo was a sprint. Artemis is something else entirely. Apollo astronauts landed near the lunar equator. This was not an accident. The equatorial regions offer relatively flat terrain, predictable lighting conditions, and orbital mechanics that make getting there and back significantly easier. The 6 Apollo landing sites were chosen in part because they were accessible. They were the safest options available, given what the hardware of the era could do. Artemis is going to the South Pole. The lunar South Pole is one of the most extreme environments in the solar system. The sun never rises high above the horizon there. It skims along just at the edge of the sky, casting shadows that stretch for dozens of kilometers across a landscape of craters and ridges. Some crater rims catch enough sunlight to remain illuminated almost continuously. The floors of those same craters have not seen direct sunlight in billions of years. Those permanently shadowed regions are the reason we're going. Orbital data and radar measurements have confirmed the presence of water ice inside them, deposited over billions of years by cometary impacts and preserved in the permanent cold. At the bottom of permanently shadowed craters near the South Pole, temperatures drop to around negative 250 degrees Celsius. Colder than the surface of Pluto, among the coldest naturally occurring environments anywhere in the solar system. Water ice at the South Pole is the resource that makes a permanent human presence on the moon possible. It can be split into hydrogen and oxygen for rocket fuel. It can be used for drinking water and radiation shielding. It is why the South Pole matters. And it is also why the South Pole is extraordinarily difficult and dangerous to operate in. The terrain is among the most rugged on the moon. Billions of years of impacts without the lava flows that smooth the equatorial regions have left behind a landscape of overlapping craters, steep slopes, and shadowed valleys that orbital cameras struggle to fully map. Apollo astronauts operated where the sun was high, and the terrain was forgiving. Artemis astronauts will operate where the sun is always low, shadows are always long, and the terrain is the most complex and least understood on the entire moon. The longest any Apollo crew spent on the lunar surface was Apollo 17, 75 hours, just over 3 days. The crews worked on a tight clock from the moment they landed. Every hour on the surface was an hour of consumables used, radiation accumulated, hardware potentially failing. The program was designed around short, intensive stays. Artemis missions are planning for surface stays of up to 30 days. That is not 3 days. That is a full month. And the difference between 3 days and 30 days on the surface of the moon is not merely a factor of 10 in duration. It is a qualitative change in the nature of the mission, the risks involved, and the demands placed on every system keeping the crew alive. Radiation exposure scales with time. The Moon has no global magnetic field and no atmosphere. Nothing stands between an astronaut on the surface and the full spectrum of space radiation. Solar energetic particles from the Sun, galactic cosmic rays from supernova explosions across the galaxy, and secondary radiation produced when high-energy particles strike the lunar regolith. Apollo astronauts received doses that were within acceptable limits for short stays. A 30-day surface mission accumulates radiation at the same daily rate, with no break for 10 times as long. The hardware faces the same problem. Every system on the surface must function reliably for an entire month rather than 3 days. Thermal cycling on the Moon is extreme. During lunar day, surface temperatures in sunlit areas can reach 127 degrees Celsius. During lunar night, they drop to negative 173 degrees Celsius. A 30-day mission experiences these cycles continuously, and every material, seal, lubricant, and electronic component has to survive them. Apollo hardware was designed to last days. Artemis hardware has to last weeks, and eventually, months. That is a fundamentally different engineering challenge, and the consequences of hardware failure at the lunar South Pole. 12 days travel time from Earth with no quick rescue possible are fundamentally different from the consequences of hardware failure in the equatorial regions Apollo visited. The spacesuits Apollo astronauts wore were engineering marvels of their era. They were also deeply imperfect, and they were only required to work for hours at a time. But Apollo astronauts reported that lunar dust, fine, abrasive, electrostatically charged particles that coat everything on the Moon's surface, was one of the most significant practical challenges they faced. The dust worked its way into suit joints, degraded seals, scratched helmet visors, and contaminated the lunar module interior. On longer traverses, Apollo spacesuits showed measurable wear. Engineers estimated that if missions had lasted significantly longer, suit integrity would have become a serious concern. Artemis astronauts will spend 30 days on the surface conducting multiple EVAs, each lasting many hours. Their suits will be exposed to the same abrasive dust, the same thermal cycling, the same radiation, for an order of magnitude longer than any Apollo suit ever was. Lunar dust remains one of the most pernicious engineering challenges in the program. It is sharp at the microscopic level. Unlike Earth dust, which is rounded by wind and water erosion, lunar dust particles are fractured and jagged because there is no erosion process on the Moon to smooth them. They cling to everything because of electrostatic charge. They are silicate-based, which means inhaled dust poses serious long-term health risks similar to those faced by miners exposed to silica dust on Earth. Apollo astronauts were inside their suits for hours. Artemis astronauts will be inside their suits for many hours, across many EVAs over an entire month. The cumulative exposure to dust-contaminated suit interiors, the wear on suit joints, and the risk of a seal failure all scale with time in ways that Apollo never had to fully confront. When Apollo flew, it was not at the peak of the solar cycle. The Sun operates on an 11-year cycle moving between solar minimum, when the Sun is relatively quiet, and solar maximum, when solar flares become more frequent and powerful, and the risk of a major solar energetic particle event capable of delivering a dangerous radiation dose is at its highest. Artemis is flying during solar maximum. The current solar cycle peaked around 2025 and remains at elevated activity. This means the probability of a major solar particle event during any given Artemis surface operation is higher than it was during most Apollo missions. A severe solar storm can push radiation levels at the lunar surface to doses approaching the threshold for acute radiation sickness within hours. The Artemis habitat will incorporate a dedicated radiation storm shelter. Warning systems built around solar monitoring satellites can provide some advance notice of incoming particle events, typically between 15 minutes and a few hours depending on the type of event. But warning time is not guaranteed. Some events evolve faster than predictions. An EVA taking astronauts several kilometers from the habitat through complex terrain that limits travel speed could make a 15-minute warning window dangerously short. Apollo crews faced this risk in principle. The difference is that Artemis crews will be outside repeatedly over 30 days during a period of elevated solar activity, where the statistical probability of a dangerous event occurring is meaningfully higher than during the Apollo era. Perhaps the single most underappreciated difference between Apollo and Artemis is lighting. Apollo astronauts worked in full sunlight. The sun was high, shadows were short and predictable. The visual environment, while alien, was legible. Craters had obvious rims. Slopes were visually apparent. The lunar South Pole is a place of permanent low-angle light and deep shadow. The permanently shadowed regions that contain the water ice Artemis is targeting receive no direct sunlight at all. They are lit only by reflected light from surrounding terrain. An extremely dim illumination providing very little visual contrast. Operating near these regions requires lighting systems that Apollo never needed. Outside the permanently shadowed regions, the South Pole terrain is still lit by a sun that never rises more than a few degrees above the horizon. This creates extraordinarily long shadows. A small rock can cast a shadow meters long. A shallow depression can be completely invisible when the sun fills it with shadow indistinguishable from the surrounding surface. A slope that appears level can hide a dangerous gradient. Apollo astronauts occasionally dealt with difficult lighting near the terminator, but they always had the option of working when the sun was higher. Artemis astronauts at the South Pole never have that option. The sun is always low. The shadows are always long, and the terrain is far more complex. The consequences of a navigation error at the South Pole, driving a rover into an unseen crater, stepping onto an unstable slope, and approaching too close to the edge of a permanently shadowed region, are severe in ways that Apollo's more forgiving terrain did not present. Apollo 13 proved that a rapid return from the moon is possible. The crew used the lunar module as a lifeboat and made it home in roughly 4 days. That 4-day return window is a feature of the orbital mechanics of travel between Earth and the moon. If something went seriously wrong with crew health, Earth was 4 days away. Not close, but not impossibly far. The Artemis architecture is more complex. The mission profile involves crew operating on the surface in a habitat, using a separate lander, conducting operations at significant distances from the lander using pressurized rovers. Getting off the surface requires the lander to be functional. Getting back to Earth requires the capsule waiting in lunar orbit to be functional and properly positioned. This chain of dependencies means emergency return from the surface is not the simple matter it was for Apollo. The timeline for emergency evacuation from an Artemis surface mission could be significantly longer than Apollo's emergency return options. Medical emergencies that might be manageable over a 4-day return become more complex, when actual time to definitive medical care could be measured in a week or more. Artemis missions plan for this with expanded medical training, more comprehensive medical supplies in the habitat, and crew members trained in procedures that go well beyond first aid. But training and equipment are not a hospital. A month-long surface stay in an extreme environment, that with physically demanding EVA work in elevated radiation conditions, creates the conditions for medical emergencies that a brief Apollo surface stay was unlikely to produce. Nobody sent an Apollo crew to the moon for a month. The longest any Apollo crew spent in space was Apollo 17 at 12 days and 14 hours. Less than 2 weeks from launch to splashdown. The crews were busy for every moment and were back on Earth before most people had time to fully process they'd been gone. Artemis surface missions of 30 days, combined with transit time, mean crews spending well over a month in deep space. This is a duration that space medicine researchers take very seriously when it comes to psychological health and performance. Isolation, confinement, a high-stress environment, and distance from family and support systems, and the psychological weight of operating in a hostile environment where a single failure could be fatal. These factors interact in ways that short missions don't fully expose. The ISS has provided extensive data on longer duration spaceflight psychology, but ISS crews have continuous communication with Earth, reasonable privacy, and the knowledge that Earth is only a few hundred kilometers below them. Lunar surface crews will have communication delays, limited private space, and Earth will be a small crescent in the sky. The honest assessment from space medicine researchers is that a 30-day lunar surface stay represents a genuine step into less well-understood psychological territory than Apollo ever entered. The mission doesn't just have to work mechanically. The crew has to remain healthy, functional, and capable of good judgment under sustained pressure for an entire month. That demand was not part of what Apollo required. None of what has been described here argues against the Artemis program. It argues for understanding it clearly. The water ice at the lunar South Pole justifies the risk. If that ice can be confirmed in quantities sufficient for extraction and use, it changes the economics and feasibility of everything that comes after. Permanent lunar bases, propellant production for missions to Mars, a sustained human presence beyond Earth's gravity. Well, that doesn't require every kilogram of water and propellant to be launched from Earth at extraordinary cost. The South Pole is harder to reach and harder to operate in than anywhere Apollo went. It is also where the resources are. Apollo proved the concept. It proved that humans could travel to the moon, work on its surface, and come home. It operated in the most accessible locations with the best lighting conditions and the shortest possible surface stays. Artemis is attempting something genuinely harder. It is going to a more extreme environment, staying far longer, operating in more complex terrain with more dangerous lighting conditions during elevated solar activity, with hardware that has to perform reliably for 30 days rather than 3, carrying crews that have to remain capable for the full duration of missions that would have been unrecognizable to the Apollo program in their scope and ambition. The people working on Artemis know this. The astronauts who will go know this. The engineers designing the hardware are not naive about the gap between what Apollo accomplished and what Artemis is attempting. That gap is real. The risks are greater. And going anyway, carefully, methodically, with every lesson from the history of human spaceflight applied to the challenge, is exactly what explorers have always done when the destination is worth the difficulty of the journey. The South Pole of the Moon is worth it. Apollo didn't end because the moon had been explored. It ended because political will and funding ran out. The last 3 planned missions, 18, 19, and 20 were cancelled. The scientific program was curtailed before it reached its most ambitious targets. What Apollo left behind was a foundation and a set of unanswered questions. The 6 landing sites, see all in a narrow band of equatorial terrain, told us an enormous amount about the Moon, but sampled a tiny fraction of its surface. The permanently shadowed regions at the poles were never visited. The geological diversity of the South Pole, which orbital data now suggests holds some of the Moon's most scientifically significant terrain, was never touched. Artemis is not Apollo continued. It is a fundamentally more ambitious program going to fundamentally harder places to do fundamentally more complex things. The comparison to Apollo is natural and useful, but it can also mislead because it creates the impression that we are doing again what we already know how to do. We are not. We are doing something harder in a more dangerous environment for longer, with higher stakes and larger ambitions. That is what makes it exploration. That is also what makes it dangerous. And both of those things are true at the same time, and will remain true for as long as human beings keep pushing into places they have never been before.